Hello all and welcome back. So in this video, now let us move forward and now write our Hashmap class using chaining, which we will be using to implement finally our Hashmap, which we can use as well, right? So in the last video, we were able to write the linked list, modified linked list class, where we have the cell key and the value operations, which I will be requiring. Now the reason we have all these operations here is that we are able to think in terms of linked list, right? Which is going to be the major node of each and every hash map element which I will create, right? Just as we saw in the visualization. Great. Now let us move forward and write our hash map. Great. So first thing from linked list from chaining, import LL node and linked list. So what I wrote, I'm just importing here so I can use that. Great. Class hash map and let's say a map using chaining. Great. One thing more, everyone, as of now, let us not focus on the overall complexity and stuff. We will be having a very good discussion on that in the next video. So right now, let's just focus on the implementation, that how exactly things are going to happen. We will understand how the complexity we are able to achieve what we want and everything. Right now, let's just quickly try to implement it in a best and the easiest way possible. Okay, great. So based on our discussion, we are going to create a constructor, and in this constructor, I will be giving the capacity, how big I want my hash map to be. So self.capacity equals capacity. We can create a self.size as well. We created this in our open addressing as well, but there we didn't add or subtract to it. So you can make that change. Okay, I think we forget to add one when we were able to insert an element, or delete when we were deleting our element. Okay, so something just we have to make sure of that. So let us now go to board and understand one more thing, everyone. See, something which we had discussion in the last video as well. Buckets array. So the buckets list or array which I have to create, this time it will be a overall continuous, right, nodes of linked list. So what I have to effectively do is each and every one of this should be a separate head of our new linked list class, right? New linked list which we have worked in the last video, which contains key and the value. Okay, great. When we used to work for none, okay, we used to write something like this. So this is how we used to define a fixed size list in the starting, analogous to array, say capacity. Great. So let me create that as well. Self dot buckets equals linked list. Okay, let me just make the name capital just to make sure of the followed convention. Linked list into capacity. Okay, great. I hope that seems fine to each and every one of you. I honestly have a problem with this particular implementation. Okay, let me explain that. Okay, let us take up this particular file and let us understand why this is wrong. This is wrong as of now. Okay, I will tell you why this is wrong. Let us understand this. See, let's say I'm making a buckets array which is this into 3. What effectively I have done is how like this code gets run in the backend. Again, these are some things which we should be very clear about, which we should have a very good idea, because they can ask in an interview as well. I must have created an head, okay, which will be none initially. Let me call that it is created on 0x100. And I'm saying that, hey, make 3 copy of this head, something like this. So my linked list, my buckets list is something of this sort, where I'm pretty sure that you will be able to see some problem. Each and every head is just pointing to the same address, which I believe is very wrong. Reason it is wrong is that if you make change into any of them, if you add an element here, it will get added here as well. It will get added here as well because they are pointing to the same thing. It's just like saying that three people, they are no different. They are just having the same name, everything same, and they work on this like they are exactly the same people. You have just made the copies. I wanted to make head of type linked list, but they should be different heads, right? So let us see that in practice as well. So pay attention, everyone. For each head in buckets, print buckets. Sorry, print each head. Right. Let us run this now and let me show you. See. Okay, it is not showing the address because it doesn't know how to print. Let us see the reference of them. Okay, identity of an object. See, all are exactly the same. So that's a very, very big problem. If we make changes into any of them, it's exactly the same as, let's say, if I add 10 here, everyone will be having a 10. So we can even see that, for example, let's say this should be linked list object. So the class, let's say if I add a element, okay, at the zeroth of, let's say add, and what we have to do, key 1, and let's say value is 100. Okay. So what we have done here, everyone, let us see. I want you all to understand these things in a lot of depth, okay, because these are the basics for anything. So for example, what we have done, I have created these three heads. I am saying that they all are pointing to the same index. If I add this key 1 and 100 here, ideally everything should be empty. The other one should be empty, right? We should not add anything here. Let's say what exactly is going to happen here. So I have added to the first one for each head in buckets. Instead of going to the ID, we have to do each head dot traverse. Okay. Great. Let us run this. Okay. Attribute error. LL node object has no attribute current. Traverse code current. Okay. So we have made an error. Let us correct this. Great. Now let's run this. See how we have key 100 in each and every one of them, right? So in each and every one, we have this particular index. How can we correct that? Let us see that. Exactly how can we correct this particular? If we make it as a list via list comprehension, right? So all of you will remember what exactly list comprehension is. If I just run this, okay, 3 times, now every time we will get a different head, and I can prove that as well. See, print each head. So in list comprehension, what's going to happen now, everyone? This linked list, it will run 3 times because it's in a loop now. So a new head will be created. And if I make it now, so let us create it and see. Now just key 1 is having this particular 100, key 1 and 100. Others are empty. Okay. So yeah, pretty sure that you will be able to understand this, everyone. We have printed the none, and let us, actually we could have just call it like this so we don't see this none as well. Great. See, so yeah, key 1 is this. Okay. Then this is the next one, which is none, and the next one. So a little bit thing to always make sure in Python. Let us now go back to our hash map. Here what we have to do, instead of doing this, I will create a internal function. Let's say self, and let me make it private only. Create buckets, where I have to just pass the capacity, right, everyone? So def underscore create buckets. In this, I will get capacity. Could not have sent that as well, but it's fine, I guess. And what we have to do, buckets equals, we can write it in a loop as well, but I'm pretty sure that list comprehension you all have studied in the previous videos. So for I in range capacity, and I can return this bucket. Great. So now we have created our bucket as well, everyone. Now let us try to add. Okay. Now let us try to add or put anything into our hash map. Let us get rid of this. Yeah. Till now, we have created our empty bucket array, which is having each and everything as a separate head. Now insert. Okay. Great. So I will be getting a self and I will be getting a key, right? Along with that, because it's insert, I will be getting a value as well. Okay, great. So the very first thing what we have to do, everyone, pay attention. If I have to insert anything into my linked list, right? If we have to insert, then let's say you ask me to insert key 1 and 100 only. Okay, or apple or 100. This will have to pass through a hash function. We'll have to pass through a hash function and it will tell me a index. We call this index as, let's say, bucket index, which we will get after compressing this through the size of my bucket, right? Once I have this hash function, I will just be adding it into my bucket array, right? Something similar we saw in the visualization as well. If I provided, let's say, 100, first it will convert it into index. So it is 9 percentage 13 and it is adding 9 here. Great. So first let us calculate the hash function, everyone. So bucket index. Okay. Similar approach we have to follow, self dot hash, let's say, function. Okay, where I will just be passing the key. Now we can write this hash function easily. Def hash function. I have a self, I have a key. Okay. We use the hash, this particular hash function in the last one, right? So hash key. We were able to write using this particular thing, which I think is a pretty good overall hash function. We can again write our own as well. Just then we will have to make sure that we handle different cases. For string, it will be having something different. For tuple, it will be different. List, of course, we cannot support. So here, what we just have to return, absolute of hash key, whatever is the absolute, and percentage self dot capacity. Okay. Same thing was happening here. If I provide 110, the hash is 110 in this case. Okay, so we are not calculating hash in some complex way. I just percentage that by 13, which is my capacity. So see, it is 6. It will get added in 6. Okay, great. Once I have my hash in the bucket index, then I have to get the particular bucket. Each bucket is a linked list head, right? So buckets and bucket index. So now I found out that hey, it has to be added on 6. It has to be added on 6. Great. Before adding, now I have to, of course, first made a search. Okay, if that is already present or not. So bucket dot search. Now this is the benefit of creating those functions, right? So see, this is the search function. It takes in from head and tell me and returns me that particular node. If it will be present, okay, I will get that node. If it is not present, then I will get none. Now my logic in this hash map will become very easy. See, if node is none, that means that I don't have this. If you don't have this particular node, then we will have to add that. How can we add? Again, bucket dot add key value. I don't have to take any problem of anything, right? Whole linked list logic I have actually written in my linked list, which I'm using for chaining. And that's the major benefit which you will see while you write the code. Now, many places, or even when I learned it in a way where every code was inside this hash map using chaining class, which make this a lot complex. Okay, but now it is a lot easy for you. Self dot, I think we have created size so that we can add by 1. Okay, not to miss it out in the open addressing, please correct that. If it is not the case, then in my node we have the overall node with that key. I can just update the value. See how easy it has become, right? Update existing key with new value. Right, everyone? So this is done. The insert is done. Now let us write for search. Okay, self and key. So I'm calling it get to not confuse it with the search here. So we will be able to get, insert, and then finally delete. Okay, great. Now let us see for get this particular search option. What we have to do. If you are asking me to check for anything, okay, 1 minute. Yeah. So if you're asking me to check for anything, let us first create a new page. Again, the idea is same. You will ask me that, hey, search this particular value. You will give me a key, let's say key 2, and say 200, or let's say 105. I will first make this key go through my hash function, right? Once I have the particular bucket, I will go to that bucket. And because I have very nicely handled the search in my linked list, I have the head. The problem just reduces to searching in this linked list, right? Searching in this linked list. So a major benefit, we actually have to do very less things here if you will pay attention. What I have to do, everyone, pay attention. First, let me copy this thing because this we will have to do every time. Buckets and bucket index, and we get that particular bucket. Now, what we have to do? Node is equals to bucket dot search with this particular key. If I'm able to find it, okay. So if node is not none, I can just return node dot value. Else, I can maybe return, hey, key not found. Right? Pretty simple now because of this particular handling. And the best part was while writing this linked list code, we don't have to think of hash maps anyway. Great. Now let us write the code for delete similarly. Okay, so def, what have we used there? Okay, it is delete here. So let us use remove here. Okay, remove. Great. So again, in remove, I will be getting a key and only a key. So let us understand on delete as well, everyone. Delete. In delete, what happens? Again, let's say you are asking me to delete key 3. Okay, now I don't need anything. In search also, actually, we will not be having any value, right? We just do the search by this particular key. This time again, also, I have to, 1 minute. Yeah. So this time again, I have my buckets array. I have to just make sure that it goes through hash function. It goes through this particular hash function. We get to this particular array. We get this particular head. Ideally, this just changes into finding that key in my linked list, okay, and deleting it. So pretty easy again. Delete in linked list, right? There we are already handling if it is there or not. So let's pay attention, everyone. See, again, it's going to become a lot easy. So let us first get these buckets again. So I get the bucket and the bucket index removed. Okay, what I'm saying removed bucket dot delete. Hey, just go and delete my key. Okay, how easy it has become, right, everyone? If we say that, hey, if removed is not none. So let us say, see here what delete does. Pay attention. If we find the key, okay, we were returning true. Okay, so we are returning true and false. Okay, great. So when we are able to delete, we are returning true. And I think one thing, self.head, we should return true here as well, right? If we find the key, then we should actually return true in both the cases after checking it. So this true can be here. Little bit correction. So this true we will be doing or returning whenever we find the key. If the previous is none, that means I have the key in my head. Okay, so let me explain you that as well, everyone. Let's say we are inserting few things. So 23 insert, then 23 plus 13, 36, 36, 49, 49, and then let's say 62 as well. Okay, so I'm just adding 13 because all of them will be having the same key. This is exactly the same thing which we are doing as well. We are just keep on adding on my overall node. When I search, let's say if I'm searching for 36, this is how I search. It will go, it went here, searching, searching, 36, it has found, it will return me, right? Next thing, when we have to delete, pay attention. Let's say I want to delete 36. It is going to search again. And this time we were saying that, hey, if we have deleted them or not, so it is returning true. That's when we have the previous here and we made this connection. If I want to delete 62, which is at my head here, then connection which will be made is something like this. Okay, everyone. So I want all of you to properly visualize and imagine this in your brain. This is the connection which we will create. Now, let us delete this and see is like this was going to happen. And yes, this is what is happening. Great, everyone. See, the thing is that if you're able to visualize properly, if you're able to think the operations in your mind, then coding always becomes a lot easy. Because coding is just writing what's on your mind. It's not something we have to remember. Okay? Great. So we are returning true here. So if my removed, if it is true, then we can just check like this. If removed equals to true, then what we have to do, everyone? First, let's delete the size. And let's print that, hey, I have removed. Okay, so let's say key and key is removed from hash map. But if this is not the case, then I should print that, hey, key is not there. Can you please check? So let's say key not found. Okay, something similar we can do here. If I want to delete 10, see 10, it will go here. Achha, 10 is there, my bad. Let us remove. Now let us delete 10 again. Okay, it is saying element deleted. Let us say 10 again. It will try to search. It will not find, so it will return false. Once I get false, I have to just send the same thing. Hey, 10 element not in a table, right? So I have to just found key not found in hashmap. Great. So I think this also done my uh, delete as well. Now, many of you might be not finding this a lot difficult. The reason is that we have divided it very smartly into two things, right? Let us write two more codes, everyone. So def underscore length. Okay, so this is what length function works on. If we write the length function, right? So it is going to be, everyone, just return self dot size. That's the reason we are maintaining this size. And def print. So these are the basic function from oops, the magic functions. So for I in range. So let us understand how print will do. Okay, pay attention, everyone. If I have to do print, I have this buckets array. Let's say it is something like this. Okay. So pay attention, everyone, what's going to happen. Each and everything is a head here, right? Whenever the head is not none, I have to just print each and every element. How can we do that smartly? I think the way we can do it smartly is we have the traverse function. So we have written the traverse function, right? So we can call it. We don't have to write any nested loop here because of the smart traverse function we have written. So self.capacity, I will go to each and every head, right? So if, let me just do it, that should be fine. If buckets, self.buckets of I is not none, then what we have to do, self.buckets dot buckets of I dot traverse. Okay, so this will make sure of everything. Let us just add it. And yeah, I think this works pretty fine. Because this expects that you will return a string, we can just return it here. So this traverse function is making sure that I am able to print everything. We will get it as in terms of bucket, but again, we can handle that, should be fine. Okay, great. I think using the smart technique of this linked list approach, we are able to finally do this. Okay, let us now try to test it out, everyone. I'm pretty sure that each and everything is clear. If you have anywhere doubt, okay, just try to see that part once again. We have used the visualization. We have tried to understand it pretty well as well. So the major approach is that everything should be a lot clear, right? So see, hash map. Let's say hash map. So this is what is the name of our hash map using chaining. So now this is my hash map, everyone. Hash underscore map dot insert insert. Insert is the function, right? Yes. So let us insert apple and say 100. One thing I think which we missed out, let us take or send the capacity as 13 by default. I'm taking it 13 because in our visualization we have 13 only. Okay. So, or let me pass 13 here as well. So it will get overall checked. We can take it as a default argument. Pretty sure all of you are comfortable with default argument. So let me add apple here. Okay, then let us see orange with 105 and then hash map dot insert banana. Okay, with let's say 200. Great. So let us first run this. We are not getting anything, not even an error. So let's hope that it is working fine. Now print hashmap dot get. Okay, apple, orange, and banana. Make sure of one thing as well. I can write it here as well. Key should be case sensitive. Why is that? Let us try to understand this quickly. Print hash of orange, hash of orange. Pretty sure they are going to be different. Let's run this one out. Run this once. Okay, so 100, 105, 200. So seems like this is working. Let me just expect, like just extend it a little. See, it is completely different, right? So they should be case sensitive for sure. Now they are same. Okay, everyone. So please make sure that you understand this as well. It should be case sensitive. Okay, don't make this error. Once I have done this, what can I do now? Let's say I delete from my hash map. It's not delete, I think remove. Yeah. So apple. And then let us try to get this again. Along with that, let us try to get the length of our hash map after deleting. And now run this. See what it is happening. We added three apple, orange, and banana. Okay, so they must have been added somewhere. Key apple is found from hash map. So, sorry, key apple is removed from hash map. Key not found. And two is the length. Okay. We can do one more thing as well. Print hash map. Okay. So this is going to run our str function. Okay. So we are getting lots of none because we have called it on traverse on I. Okay. But we are able to see that, okay, orange and banana is here. If this bucket is not none, each and every bucket, if it is not none, so we might have to check that, but I hope you're able to see. So I think there should be 13 in number, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So it is just printing everything. We might have to check exactly. There are just one thing more I would like to explain and check. Let's say we make a single overall, single length hash map. Okay. Now let us try to print this, everyone. Okay. So pay attention. I will be printing it after inserting as well. See what happened. Banana 200 is the first, last one. Orange 105, apple 100. And then we have the none. Then 100, 105, 200. 100, 105, 200. It is in order. Apple, orange, and banana. Key apple is removed. Key not found. Size is 2. The length. And the final hash map. Okay, it's not a linked list. It's a hash map. 200, orange. Now what is happening here? We just have a single overall node. Oh, sorry, single node. Yeah, single node of head, linked list head in my hash map. Well, if that is the case, we will keep on adding in each and everything. Now, many of you might have a doubt, which is that basically on the complexity, right? That if we have a single node, then how can we say that it is O of 1? Before implementing everything which we learned about our dictionary and the hash map or hash table, the major benefit was that we will be able to do everything in big O of 1, right? But here, if let's say it is a single uh, length hash map, or normally in 13 size hash map, we are adding, let's say 130 elements, then won't it be a problem, right? Now in the next video, we are going to discuss each and everything regarding the complexity and also how can we correct the same. Okay, so in the next video, we are going to do that, everyone. Few changes will be required in this structure. Till then, I want each and every one of you to write this complete code from scratch. Okay, I honestly have made it a lot easy because if you will see this code, I don't think you will find it this easy anywhere. So please make sure that you write this code, the linked list code as well, and this as well. And also add that set item and get item. So we saw the same in the open addressing, right? Where we were able to add using hash map, something like this. So I can say pineapple equals 100. It will fail right now. Name hash map. See, it will fail. Hash map object does not support item assignment, right? So how can we correct that? I can just do it for this set item, and you have to do for get item then. Okay, so self key, we will just be getting the key and the value, and we have to just call self dot insert key and value. See, everything is fine now, right? All. So yeah, pretty sure that you must have enjoyed this coding. From my end, I have tried to make it a lot easy because this is normally found to be a lot complex, like the most difficult code when even I was learning coding. So on that note, just please try to just implement this once, and in the next video, let us now talk about the complexity involved.